observing our surroundings, we often encounter waves in various forms. Consider an instance when you witness a companion plunging into a swimming pool. Waves emanate from the point of their entry, rippling across the pool's surface. This observable phenomenon is the effect of the jumping force compelling water molecules to oscillate. Similar oscillations are instrumental in the propagation of light and sound, demonstrating how waves serve as carriers of energy. Sound waves have the remarkable capability to permeate through gases, liquids, and solids, although they are unable to traverse empty spaces. The genesis of sound waves is linked to vibrations. Imagine the act of rapping on a door, a movement that prompts molecules in both the door and the surrounding air to tremble. These oscillations, in turn, stimulate neighboring particles to vibrate. Once these tremors disperse through atmospheric gases and reach your auditory system, you perceive the distinct sound of a knock. Frequency, the rate of these particle vibrations, measures how rapidly they vibrate. In other words, frequency quantifies the number of sound waves produced each second. Higher frequency denotes rapid vibrations, resulting in a sound with a high pitch. On the contrary, light waves differ significantly from sound waves in that they can journey through empty spaces. This is attributed to the fact that light waves are not reliant on particle vibrations. Light is an instance of an electromagnetic wave, possessing both electrical and magnetic influences. Occasionally, such electromagnetic waves are termed as radiation or rays. The speed of light waves surpasses all in the vacuum of space, with light traveling approximately 1,000,000 times faster than sound. This speed difference becomes apparent during a thunderstorm, when lightning is visible before the thunderclap is audible. Light energy, upon encountering matter, can transform into heat energy. Materials classified as opaque, such as the majority of fabrics, wood, concrete, and metals, have the ability to absorb light. Such materials obstruct light passage entirely, with a fraction of the light energy being absorbed. Darker shades absorb more light, leading to greater heat generation compared to lighter colors. Hence, on warm sunny days, it's advisable to don lighter hues. Semi-transparent or translucent materials, like tissue paper and certain garments, permit partial light passage while absorbing a portion of it. Transparent materials, including glass and water, almost entirely allow light passage without absorbing it. Here's an overview of the effect of materials on light. Transparent objects allow all light to pass through them. Translucent objects allow some light to pass through them. Finally, opaque objects allow no light to pass through them. Reflection is another intriguing phenomenon where light, instead of absorption or passage, bounces off a surface. The smoother the surface, the higher its reflection potential. Reflective surfaces are easily found in objects like mirrors, smooth metals, and dishware. A mirror, for instance, reflects the room's light back to you, enabling you to see your reflection. Lighter colors, since they absorb less light compared to dark shades, reflect more light. This principle becomes evident in a dimly lit room, where lighter objects are more visible. Reflection and absorption processes explain our perception of colors. A blue book, for example, absorbs all colors except blue, which it reflects back to our eyes. Ever noticed how a straight straw appears bent when immersed in water? This optical illusion is the effect of light changing speed and hence direction when transitioning between mediums. In this example of a pencil, the mediums are air to water. This light-bending phenomenon is called refraction, which also occurs with other materials like glass. If you look at this diagram, you'll notice the bending or change in direction of light waves when they encounter the water. To this boy, the fish will appear more shallow than it actually is.